This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning. Hope you had a good weekend. In the last lecture, we discussed the bipolar current mirror circuitry. So why do we need current mirror? What is a current mirror? Why do we need a current mirror? So today we will be discussing about current mirror, but then how it will be applied in the circuit. How can you use current mirror to bias your circuit? Then we also need scaling up, because golden current may be 1 milliamps, but your requirement may be 2 milliamps. How to scale up? Or sometimes scaling down. Your golden current from the band gap reference might be 3 milliamps, but your circuit need only 1 milliamps. So you need kind of a scaling down or scaling up without losing the property. So recap. So we discussed how to make a current mirror in the last lecture. So what we have done is we have got the golden current. So I use golden current because this current is from the band gap reference. That golden current is coming. That is going to the collector of a transistor. Then collector we connect it to the base so that we get some bias current. And then when we have this circuit, what is happening is this current will decide this VB, and then if we can connect another transistor, then what we can get is we can get the same VB so that we get the same current here. And then this circuit, we have proved that it can mirror the current, the golden current. We also proved in the previous lecture that the I copy is independent of the temperature or any of the circuit parameters. Then, so we have got 2 milliamps. So that is the golden current. This current is coming, this part is coming from the band gap reference that you have connected to this transistor topology so that you can get a copy of this golden current. So if this is 2 milliamps and then if we neglect this current means your 2 milliamps is coming down to this point. From this point actually the current is branching to 2. But then our assumption is we are going to assume the base current equal to very, very small. This base current is very, very small. This base current is very, very small. So that this current, the current that is coming from this part to this point is neglected, very, very small. So what is happening is 2 milliamps is coming to this point, then 2 milliamps is coming to here, collector, and then coming out to the emitter. So 2 milliamps is coming to this point. No current is flowing to this direction for time being, because that current is anyway, it is a very small current, because this is in the milliamps region and here it is in microamps region. Obviously that will create a small error, but at the moment we are not taking into account that error. So at the moment what our assumption is the base currents are neglected. So this current is neglected, this current is neglected, so that this current, the current that is tapping from the 2 milliamps, that is neglected. So 2 milliamps is coming to this point, and then 2 milliamps is coming down as collector current. If this is 2 milliamps and if we neglect all the base currents, what is the current here? It will be definitely 2 milliamps. So you get 2 milliamps here. So if we connect 3, because we are neglecting the base currents, so we have got 2 milliamps here, then I will be connecting here you get I copy 1. Then again this point I am going to connect to the base of another transistor. This point I am going to connect to the base of another transistor. Then what will be the current? What will be I copy 3? So two answers. The golden current is 2 milliamps. So you can have 1 milliamps. How many of you think? 2 milliamps. Yeah, all 2 milliamps. Why? Because this is 2 milliamps. You are neglecting the base current. When you have 2 milliamps, then 2 milliamps is coming down, then you are getting a VB. So this VB is same. VB of Q1 is same. VB of Q2 same as VB of Q1, because voltage between this point and this point, which is same for Q1, Q2, Q3 and Q reference. So that if you got 2 milliamps here, then you are going to get 2 milliamps here, 2 milliamps here, 2 milliamps here, 2 milliamps here. So your I copy, which is equal to saturation current ISJ of jth transistor divided by IS reference, means if you got only 2 transistors, this is a saturation current of this Q1, and then this is a saturation current of your this transistor, reference transistor, Q reference, and then if both are identical, then we can cancel out. So I copy equal to I reference. Multiple copies of I reference, that is our golden current, can be generated at different locations, see, at different locations, by simply applying the idea of current mirror to more transistors. So we can apply this to this idea to more transistors and generate I copy at different locations in the circuit. Now scaling. So scaling is very important, because the golden current is 2 milliamps, but then we may need a different current here, not always 2 milliamps. Then what we will do? If this is 2 milliamps, you will get 2 milliamps here. So how can I get 6 milliamps? So what will you do? Yeah, so you can connect these things parallel. You got 2 milliamps, 2 milliamps, 2 milliamps. So if you connect together, you get 6 milliamps. So that's how we generate it. Then we will not draw always like 3. So what we will write is, we will write 3 times area of the transistor, because here what you have done is when you have connected 3 transistors, your area increased. So your area increased thrice. That is the reason you are getting more current, 6 milliamps. And then we write 3 times AE, because sometimes you will be connecting 10 transistors. Then you may need a A1 size paper, 10 transistors connected together. We don't need to draw that one. You can just draw one transistor and write 10 times AE. So the logic behind this, your collector current equal to IS exponential VB by VT, and then ICT. So what is a collector current? Which is equal to here, the collector current exponential VB by VT IS1 plus IS2 plus IS3. So your total collector current. But then your IS, saturation current, that is depending upon the area. So that is the reason when you connect 3 transistors in parallel, what you are doing is you are increasing your area thrice. So that is the reason we can write 3 times area. So that is the reason here, because this is proportional to the area. So when you connect 3 transistors in parallel, then we are increasing the area of the transistor. So collector current increased because area increased to 3 times AE, because IS1, IS2, IS3, if all are identical, you get 3 times IS. So 3 times this area. So I copy, which is equal to N times I reference. So we can scale, you can scale up if you connect transistors in parallel. By scaling the emitter area of Qj N times with respect to Q reference, I copy J. We write this J because we may be connecting so many. Also N times larger than I reference. This is equivalent to placing N unit size transistors in parallel. See, so if you want to scale up, you can connect transistors in parallel. Then we will be writing 3 times area. Then I have shown this equation because then somebody might ask you, why are you writing 3 times area, not 3 times something else? So 3 times area, the logic behind this, when you connect 3 transistors in parallel, what you are doing is you are increasing the area. Okay, now we will do a group work. Design current mirror circuits. A multi-stage amplifier incorporates 2 current sources. So you need 2 current sources. A multi-stage amplifier incorporates 2 current sources of value 0.75 milliamps and 0.5 milliamps. So you got 2 amplifier circuit. You need golden current of 0.7 milliamps and 0.5 milliamps. Then you got only one band gap reference. Your band gap reference is 0.25 milliamps. Design the required current sources. Neglect the effect of base current for now. So you don't have to take into account the base current. So the question is, you got only a one band gap reference that is giving you golden current, that is equal to 0.25 milliamps. So that is your golden current. Using this current, you have to generate 2 other currents, 0.75 milliamps and 0.5 milliamps. How will you generate? So you have to generate 0.75 milliamps from golden current 0.25 milliamps. So how many transistors are required? 3. Yep, that's correct. So 3 transistors. So first we will do is, this is a current mirror. So we got VCC, then 0.25 milliamps, I reference. This is a current from the golden. This is a golden current. That is current from the band gap reference. Band gap reference. So you are getting 0.25 milliamps is coming, and using this circuit we are generating a I copy. So when you generate I copy, if you connect only one transistor, here you get only 0.25. If you connect only one transistor, you get 0.25. But your requirement is 0.75 milliamps. That is, then you have to connect 3 transistors and connect together. So 0.25. This will generate 0.25, this will generate 0.25, this will generate 0.25. If you connect together, you go to 0.75 milliamps. Then you need to generate 0.25, and then you need 0.5 milliamps. So you need 2 more transistors. So how will you connect it? From here you can connect 2 more transistors. So that is how to generate 0.5 milliamps, simple. So from the golden current you go to 0.25 milliamps. From here you can connect 2 more transistors, because this transistor collector will give you 0.25 milliamps. Here will give you 0.25 milliamps. When you connect together, you get 0.5 milliamps. So this how we will be generating. Now your question is how you will be connecting this to an amplifier. That we will study in the coming lectures. So at the moment we will study step by step. First we studied current mirror. Then we studied how can we design a current mirror. Then now we are studying how to scale up current mirror currents using the current mirrors. Now we will study scaling down. Then we will be connecting to a circuit. So the connecting to the circuit will be studying towards the end, which makes sense. Now the problem is you can scale up. You got 0.25 milliamps. From that you can get anything above this one, 0.25. Then you can generate 0.25, 0.75, 0.5 milliamps. So you can scale up. Anything above 0.25 you can get it. But now there will be requirement. Your golden current may be X milliamps, but then your requirement will be less than this one. So how will you generate a fraction? You know my question? PNP. Any other idea? Anyway, good way of thinking, yes, PNP, but then we need a simple solution. Maybe simple solution with NPN. So what you meant is you connect like this together. Yeah. So if you got 0.25 here, then when we connect to, we are getting 0.5 milliamps, but then my requirement is 0.1. Well, maybe you came close to what the answer. When you connect together, we can solve this issue. Maybe I'll draw it so that it makes sense. So what we are trying to do is, so you got your Q reference. So that is our reference. Then that is so this is a golden current. So maybe that is, I'm going to take 2 milliamps. So this is coming from the band gap reference. Then how we are generating is, so we are going to connect this to the base, and then what is happening is this 2 milliamps is coming, and then this we are getting a VB, and then we are connecting another BJT here, and then we are getting I copy, and then this is 2 milliamps provided we neglect base currents. So base currents of what? This base current we are neglecting, and then so we get around 2 milliamps. So here if we connect maybe one more transistor here, we can add up 2 milliamps, we can make 4 milliamps, 6 milliamps. Now what we need is, maybe I need only 1 milliamps. I need to generate 1 milliamps, that current, the golden current. Here it is 2 milliamps, but I need 1 milliamp golden current. Then here I already said that this base current is neglected. This base current is neglected, means if your 2 milliamps is coming to this point, maybe before that I should ask you a question. So I am going to draw another transistor. So here 2 milliamps is coming. So that is there. And so that I call it as IC. Here I call it as IC1. Okay. Then maybe some current it is going. So nothing to related to this one. Maybe that is IX. So if that is the case, what is my collector current? IC or IC1? But somebody said IC. IC or IC1? Yeah. So you have to be careful when you have these type of diode connected connections. The collector current is the current that is coming here. If there is a connection here above, that is not the collector current. So we can say that IC equal to IC1 if your IX equal to 0. Means if you neglect the base current, we can say IC equal to IC1. So that is the reason here your 1 milliamps, that is your golden current, which is equal to your collector current, because 2 milliamps is going here. Because we are neglecting this current for time being, because that is very, very small. And so your golden current equal to collector current, that is the reason you are getting here 2 milliamps. If that is not the case, what will happen is a little bit go this way, and then this current will be less than 2 milliamps, and this is actually duplicated here. You know what I meant? See, here this is 2 milliamps. Then IC1 is going to be 1.99 milliamps. And then here when you connect your transistor, another transistor here, identical. Then this 1.99 milliamps, so your IC Is exponential Vb by Vt, so that your Vb equal to, what is Vb? Yeah, so Vb proportional to ln Ic by Is. Then, so then when you have got 1.99 milliamps, that is this 1.99 milliamps. So the corresponding Vb, what you are getting, this Vb is because of the 1.99 milliamps. Then what is the current here? 2 milliamps or 1.99? Yeah, so this current will be 1.99 milliamps. So that is very important concept, because this collector current will decide what is a Vb here, because that Vb we are using for generating collector current for this transistor. So that is the reason we are getting only 1.99 milliamps. But immediately when we say that these both are same, we are neglecting this current. That is the reason we are getting here 2 milliamps, then here 2 milliamps. So otherwise this collector current is mirrored here, not the reference current. So that's important. Okay, so we will come back to our question. Here now we got 2 milliamps, here I got 2 milliamps. My requirement is here I need 1 milliamps. If I need 1 milliamps, what I can do? Yeah, so if I connect another transistor here, if I connect another transistor in parallel, then what I can do is, see, then this 2 milliamps current is coming, then 1 milliamps will go here, 1 milliamps will go here, so that I can get a fraction. So I can, I got some neat drawing. So 0.28 milliamps, that is your golden current. Our requirement is 0.08 milliamps for one of your amplifier circuits. So how to generate? Now if you look at the relationship, your I copy equal to 1 by 3 times I reference. So because this 0.08, which is equal to 0.25 divided by 3, then we can connect 3. So when you connect 3, what is happening is 0.25 milliamps is coming here, then divided by 3, 0.28 divided by 3, 0.08 milliamps will go through this collector, 0.08 will go through this collector, 0.08 go to this collector, and then your Vb is corresponding to 0.08 milliamps. That is a Vb that you are getting. 0.08 milliamps will decide what is a Vb value. Then here you get 0.08 milliamps. A fraction of I reference can be created on Q1 by scaling up the emitter area of Q reference. So here what we are doing is we are splitting the current using transistors connected in parallel this area, so that I copy here you can get a fractional value. So different mirroring ratio. Example means now you need to scale up and scale down. Design the current mirror circuit to generate two currents equal to 50 microamps and 500 microamps from a reference of 200 microamps. So reference, that is your golden current. The current from the band gap reference, that is 200 microamps. Now you have to generate two currents, that is 50 microamps and 500 microamps. So 200 microamps, obviously 500 microamps is bigger, so you can scale up. But then 50 microamps you have to scale down. But then when you scale up and scale down, you have to do it in a proper way, because you don't have to use more number of transistors. So how will you do it? So 0.2 milliamps. And then first we are going to generate 0.05 milliamps, which is equal to 50 microamps. Then we have to generate 500 microamps, which is equal to 0.5 milliamps. So we already studied the relationship 0.2 milliamps and then 50 microamps. What is the relationship? 1 by 4th. So if you connect 4 transistors in parallel, here 4 AE, maybe you don't have to draw 4 times, rather you just write here 4 times AE, like here we write it. 4 times AE, then what will happen is 0.2 milliamps is coming, and then it is splitting equally into 4 because the transistors are identical, and then in the each one you will get divided by 4. so that you can get 0.05 milliamps. Then if you get 0.05 milliamps, in order to get 500 microamps or 0.5 milliamps, you need 10 transistors connected in parallel. So that is the reason from here we are connecting 10 transistors so that you get 0.5 milliamps. It's very straightforward. So you can scale down and you can scale up. Using the idea of current scaling and fractional scaling, I copy 2 is 0.5 milliamps and I copy 1 is 0.05 milliamps respectively, all coming from a source of 0.2 milliamps. Means here first we saw our source is 0.2 milliamps, and then what you need is 0.05 milliamps. So that is 4 times less. So you connect 4 transistors in parallel, so that here each transistor we will be getting 0.05 milliamps. So then when you connect a transistor here, that VB will give you 0.05 milliamps here. And then when you connect from here, your VB, this VB will give you 0.05 milliamps. But then you have to generate 0.5 milliamps. So here, so that is 10 times. So that you are connecting 10 transistors in parallel, so that and connect together all the collector. Then you get 0.5 milliamps. That's how we do. Yeah, so I'll be continuing. All these are in a recap. Yep. So now what we did is we have neglected the base current. Here when we have designed this one, just now we discussed 2 slides before, the first example. So here what we have done is we have got a band gap reference of 0.25 milliamps. And then you have generated 0.75 milliamps, you connected 3 together, and then 0.5 milliamps, you connected 2 in parallel. But in all these cases, what we have done is we have neglected the base current. As I said before, actually the point 0.25 milliamps is coming here, and then your collector current coming down is a little bit lower than 0.25 milliamps, because some current will flow through this one, and then that will go for biasing these transistors. But we have neglected that bias current. So when we neglected our base current, then what is happening is your reference current equal to your collector current, which I already discussed using my document camera. Your reference current and collector current are same because you are neglecting this current. But if you don't neglect this current will be less than your reference current. What you are getting here, the copying, that also will be less than that. So at the moment this is the case, we neglect that current. But if you don't neglect that current, what will happen is, suppose 0.25 milliamps, that is your golden reference, and then maybe only 0.20 milliamps you are getting here. Remaining it will be taking for biasing these transistors. If base current is not neglected, then there will be an error in the copy or error in the mirroring. There is an error. Means what is error? The error is this is the current that will be mirroring, which I already explained using the document camera. This collector current will be mirroring. If this is the case, if this much current is losing here, then my question is, what is the current here you are getting? Yeah, 0.6 milliamps, you don't get 0.75 milliamps. So that is an error because you are taking into account the base current. So if base current is not neglected, you get always less. See, 0.6 you get 0.4 milliamps. Suppose 0.01 milliamps base current required for each transistor, then there is also another problem. If that is the case, you have got here 0.060 milliamps, 0.04 milliamps, then there is also another headache, because here you are getting suppose you are getting 0.05 milliamps. Then what I have noted is, suppose 0.01 milliamps base current required for each transistor, means for this transistor the required base current is 0.01. And then this transistor 0.01, this transistor 0.01, 0.01, 0.01, 0.01. So how many transistors are here? Then the 6 transistors need 0.06 milliamps, but then we have got only 0.05 milliamps here. You know what I mean? Means when you connect more, like you are generating here 0. So when you connect more transistors, then this current will limit how many transistors you can connect. You know what I meant? Because if, then what will happen is this current will be less than the required current. But if you neglect the base current, you are in the ideal world. You can connect infinite number of transistors and you get the copy. But in the real case, what is happening is because each transistor needs a minimum bias current, then this current, whatever you are getting, you should be able to provide the biasing. Otherwise, you can't connect. Maybe here, if you are getting only 0.5 milliamps, you can't connect the 6. You can connect only 5 transistors. Then, here also the same thing applies, because if you, yes. Yeah, so here at the how many we got? 1, 2, 3, 4, 5, 6 transistors. So that's the reason I have written here. Then 6 transistors need 0.06 milliamps. Yep.
Is it because you specified what the IC of the QREF to be equal to?
Yeah. So here what we are getting is 0.02 milliamps, because here this is an example. So 0.02 milliamps, and then you are getting only 0.20 milliamps, and then here I have taken 0.05 milliamps to tell you that then you can't connect the 6 transistors. So this value might be different. Maybe this value, maybe you are getting 0.25 milliamps, and then here this value, depending upon this transistor, all the biasing, maybe this value may be a different value. Then even if you get to say 0.06, then this may be just sufficient for this one, but then you can't connect one extra. Yep. So means this current may be any number. So my point is this current may be x milliamps, but then the point I am making is when you have x milliamps, then that x milliamps should be able to provide base current for all the transistors that you connect. Means that is not possible if you got, because each transistor need maybe y milliamps, then your x milliamps will be immediately divided up, and then there will be a maximum number. Beyond that you can't connect it. So then again the scaling down, again there will be error, again same applicable to scaling down. Then how to find out the error? So we are going to find out the error. How to find out the error for the mirroring when you take into account the base current. So in order to take into account the error, what we do is, this is our golden reference, that is I reference, that is coming here. Then from here your current is coming, and then coming to this point, then branching to 2. This part is for biasing this transistor, base current for Q reference, and then this current is for your Q1. Then if this is I reference, and then that is your reference current, and this is the collector current of Q reference, then I have written here I copy divided by n times beta, here I copy divided by beta, and then here I have written n times AE. So what I am trying to do here is, I am going to get the general case. In the general case means here you may have n transistors, here you may have n transistors. You know what I meant? Because this derivation should be applicable to both the scaling up and scaling down. So in order to take into account both scaling up and scaling down, we will be putting the n number here. So when you put n equal to 1, we will start. Suppose n equal to 1. So when equal to 1 means only you have got AE. So here it will become I copy by beta, I copy by beta. Means both the currents are same. I copy by beta, I copy by beta, that is a base current. Symbol. So this is your I copy, that is a collector current of Q1. If this is a collector current, what is a base current? I copy by beta, because your base current equal to collector current divided by beta. But then here again same, if you got only one transistor, then this current also is I copy by beta. Suppose you are using some fraction and then you are connecting maybe 2 transistors, then your I copy will become I copy by 2 times beta. So in order to take into account that fraction, that's the reason we are using n. Same with this n. Then, so when you derive the expression IB1, so what is IB1? Base current of Q1, that is equal to I copy by beta, because I copy is a collector current. Collector current divided by beta equal to base current. IB reference, the base current for the reference transistor. Again, that is equal to I copy by beta, but then we got this 1 by n because our assumption is we are connecting n transistors here for getting the fraction, because we want to take into account that also in this equation. So when only one transistor, n equal to 1. Then we are going to write KCL at y. So when you write KCL at y, what you will get? I reference, that current is coming to this point and then branching into 2. Then I reference, that is equal to IC reference. IC reference is this current. The reference current of this Q reference, the collector current of Q reference is IC reference, plus this current. But then this current is the sum of these two currents. So that is the reason I copy by beta into 1 by n plus I copy by beta. I have put the arrow so that it makes sense. So that is the collector current of your Q reference, IC reference. And then this is this current, and then this is this current. And then that this, both the currents are coming from, we are tapping from here. So that is the reason here, this is a sum of this current and this current. Then I copy. So I copy equal to n times IC reference. See, IC reference, which I already discussed. I copy will become n times IC reference. N equal to 1 means you are connecting only one transistor. Then IC reference, I copy equal to IC reference. So if you connect n transistors here, then you are adding up all the numbers. For example, this is 2 milliamps. And then if you got only one transistor here, your I copy equal to only 2 milliamps. If you got two transistors here in parallel, your I copy will become 4 milliamps. So that is the reason we are using the n. N means the number of transistors we connect in parallel in order to scale up. And then IC reference. So IC reference equal to I copy by n. Then I copy. What is I copy from here? So now you got IC reference equal to I copy by n. You can substitute here, so that you are getting here I copy, here I copy, here I copy. Then we can take I copy out, and then when we rearrange, we get I copy equal to n into I reference divided by 1 plus 1 by beta into n plus 1. So that is a relationship between I copy and I reference when you take into account base current. If you don't take into account base current, what is the relationship? I copy equal to n times I reference. If you are only using only one transistor here, I copy equal to I reference. But when you take into account the base current, I copy equal to n into I reference divided by 1 plus 1 by beta into n plus 1. So as the copied current n increases, so does the error in I copy. Means if you are connecting so many transistors, means if you are not connecting here, you are connecting maybe 10 transistors, because you are using 10 times maybe this current. Then from here you are tapping, again you got other branches, and then you are using so many transistors here in parallel in order to make scaling. You know what I meant? If you are using so many transistors, what will happen? Your n equal to a bigger value, n equal to a bigger value. When n equal to a bigger value, then your I copy and I reference, the error will be more. Your I copy will be different from the I reference value. Then if n equal to 1, means you are using only one transistor. You got 2 milliamps here, then you are connecting only one transistor. Then here you don't get 2 milliamps, but you can get close to 2 milliamps. Why? Because if you put n equal to 1, what will happen? I copy equal to I reference. Your 2 milliamps divided by 1 plus 1 by beta. Beta equal to maybe 100. And then n equal to 1. So 2 by 100, which is equal to 0. How much is 2 by 100? Yeah. So 1 plus 0.002, then you got here 2 milliamps. That is, approximately 1.99 milliamps. You know what I mean? When n equal to 1, you are approximately getting the same as I reference. I copy is approximately same as I reference. But then when n is increasing, your error is increasing. And then this is a problem with this type of current mirror circuit. So then this current mirror circuit, there is a problem. Means when your transistor number increases, you have actually two problems. When you have more transistors, your error will be more. Secondly, there is also a fan out problem. Fan out means the current you are getting here, that should be able to power the remaining transistors. That also is a problem. Then how to overcome this issue? So MOSFET. So if you are using MOSFET, okay, beta will be infinity. Yeah, you don't need a base current. That's a good thinking, because as what he said is if you replace this BJT with the MOS, then you don't need this base current, because in the MOS it is in the picoamps. See, okay, that's a very good solution. And then my question is, I don't want to use the MOS. I want to solve, this is, we are talking about BJT. We are solving issue with the BJT, then we have to solve with the BJT. You can't bring in MOS now. Because I have fabricated a chip using BJT, so what I will do? I can't replace it with MOS. So if this is the situation, what you can do? So what is the problem here? Give a separate source for base current is an option. Yes, so that can problem solve, because here the problem is from here you are getting only a limited current. That limited current should be able to bias all the transistors. So if you can pump more current, maybe this problem can be solved. So if you want to pump more current, what you can do? Here you want to pump more current in. So what you can do here? BJT, yes, that's all. See, now you learned how to think. Improved design, you can solve issues. So improved design, what we will be doing is from here we will be taking that current as a base current, and then emitter we will connect to this point. Then how we will improve the current? Because this current, whatever the current is coming here, that multiplied by beta is the current here, your emitter current, so that you are getting more current. And then here if you assume your collector current equal to emitter current, which is almost same, and then we are going to derive the expression and show that error is less here, because you got more current here. So our assumption is ICF, collector current of this transistor, is approximately equal to the emitter current of this transistor. So then we are going to start the equation. KCL at X, so this is a X point. So if you write KCL, ICF equal to IEF, we already said this collector current equal to emitter current approximately. So your ICF equal to, that is for this transistor QF, I copy by beta, because that is this current, I copy by beta into 1 by n, this current. So this current is coming and then branching into 2, and then that is this current, ICF. Actually this is emitter current, but then our assumption is emitter current is approximately equal to collector current. ICF, which is equal to I copy by beta into 1 plus 1 by n, just to rearrange it. Then we are going to apply, we know that I copy equal to n times IC reference. Now, what is IBF? What is the base current? So if you know the collector current, what is the base current? So divided by beta. So this ICF divided by beta, which is equal to base current. So we know that now this collector current, what is the collector current? And then if you know the collector current, in order to find out this base current, it is easy, collector current divided by beta. So you already got the collector current, so divided by beta, so it will become beta square. So that is a base current of QF. Then we are going to apply KCL, Kirchhoff's current law, at P, this point. So when you apply this point, what is the Kirchhoff's law? So you got I reference is coming, then IBF means QF, base current is going this way, then IC reference is coming down. So you got three currents. I reference equal to IBF, that is a base current of QF, and then this is a IC reference. And then when you substitute the values, because IBF, we already got this part, I copy divided by beta square into 1 plus 1 by n, plus IC REF, what is IC REF, which is equal to I copy divided by n. Then your I copy will become n into I reference divided by 1 plus 1 by beta square into n plus 1. See, so now what you have got extra is beta square. So now even though your n is big, because your beta square, your error is small. And then you can also connect this to so many transistors, because this current is now much bigger, not just tapping a little bit. This is much bigger current. So you can connect to so many transistors, and then the error is reduced by beta square. Even by looking at this equation, because previously what you have got is only the beta, the same equation, see, n reference divided by 1 plus 1 by beta into n plus 1. Now what we have got is beta square when you added a transistor. See, n reference, n into I reference divided by 1 plus 1 by beta square into n plus 1. Even by looking at this equation, like you know the previous issue, this issue, you know the previous issue, here it is n into reference divided by 1 plus 1 by beta into n plus 1. So this was the problem. Even somebody came up and said, I solved this issue, and then this is the equation. When you see this equation also, you can find out how that person solved it, because there is one beta is coming to effect. Then you can think of, okay, that person used some transistor and making use of that amplification beta. You know what I meant? So that's how we solved this issue, the error mirroring problem. Because now you can see, because of the beta square, beta may be 100, then beta square is 100 square. So you are much better. This circuit is much better, and this value will be approximately equal to your I reference than this one. Second thing is this current is limited, what you are tapping directly, and then you can't connect to so many transistors, because this current will not be able to provide a bias for all the transistors. But here this current is 100 times maybe more, because of your beta is 100. So you can connect to more transistors. Because of QF, the base currents of Q reference and Q1 are mostly supplied by QF rather than I reference. Mirroring error is reduced to beta times. Sorry, I didn't get, sorry. No, because this is our I copy, and then here, because we are connecting so many transistors, that's the reason we use NAE. And then so I copy, which is equal to I copy by beta, and then this is I copy by n times beta. Why? Because here we are connecting so many transistors in parallel here. Because here when you connect the parallel, I know your question, so when you connect here in parallel, the problem is we need this I copy by n times beta, because your collector currents are going to be different. But here, even if you connect your so many transistors in parallel, your collector current is not going to be different. All the collector currents are same. But here, the collector current, when you connect so many in parallel, your collector current is actually divided. Like if you connect two, this collector current and this collector current both are going to be half-half. Because if you are getting I reference, here if you are connecting two transistors, in order to scale down, then this collector current will be I reference by 2, here it will be I reference by 2. So that is the reason we are using here I copy by 2 times beta. But here what is happening is you connect so many transistors in parallel, your collector current is same, because that is a copy. So that is the reason we are using here I copy by beta. So generation of I reference for NPN current mirror. Now we know how to scale up, scale down. We know what is the problem with omitting a base current, and then we came up with some idea so that the error is minimum. Now we are going to apply this to the circuit, because that is our application. So maybe this part I will discuss in the next lecture, how to apply this to the circuits. Yeah, sure.
Which is